example. This is not giving me the function sine of x. It's just giving me information about the derivatives of f. But it does say that f is a function with continuous derivatives. So that helps me a little bit to be able to develop this as a polynomial, right? So it says, write the Taylor polynomial of degree 3, and f is centered at 2. So I am going to build this using that formula that I was given. We are approximating f of x by doing a third degree polynomial. This represents the degree, not the number of terms, okay? It's got to be a degree. So the first thing I need is the center. The center is at 2. That's going to be very important. That means everywhere up here I see an x minus c. That c value is the 2, right? That's why they gave me information about f of 2, f prime of 2, etc. So it starts with f of 2. So f of 2 is just 3. Then I need f prime of 2, so that's going to be, I'm adding the term, but because it's a negative 4, I'm going to do plus negative 4. It's going to be times x minus 2, technically to the 1 power, but you don't have to show that. Plus 7 f double prime x minus 2 squared over 2 factorial. Right. Plus, and then you've got negative 5 x minus, 2, excuse me, 2, got ahead of myself, 2 cubed over 3 factorial. Now remember, we wanted a third degree, which means that this x has to be cubed, and it doesn't become cubed until I get to this fourth term. So this is my third degree. You wouldn't have to rewrite this if you can clean it up a little bit, but I will rewrite it just to make sure. Again, this is an approximation. Let me write that real quick, okay? P of x is an approximation. We're not saying f of x is this. Not yet anyway. Okay, because we have a certain defined number of terms in here, so it's not infinite. So we're just saying that f of x is close to this for a certain number of terms. So it'd be 3 minus 4, x minus 2. You can do 7/2, but there's no need to get rid of the factorial. You can if you want to, but reducing is not necessary. Again, you can make this 3 factorial a 6, but it's not required for accuracy, right? You don't have to simplify at this step. Now, this is a scenario where they gave me the important information, but sometimes they don't. Sometimes you have to build these polynomials. So this is asking me to build a fourth degree Taylor polynomial for e to the 3x, okay, and it's centered at 2. So the first thing that we're going to want to do is we're going to want to take the derivatives at 2. This is how I build, okay, so we're going to build this using the formula. Build using formula. So that means I need f of 2, f prime of 2, f double prime of 2, etc. But remember, all I was given was f of x. So I need f prime of x, f double prime of x, f triple prime of x, all those. So I start there, and then I immediately write my center, because I'll mess it up if I don't. So f of x, and then this is basically what's happening at 2. I'm going to move that down just a little bit. So this is your f of 2, right? So this would be e to the 6th. So I'm going to build all the derivatives. Now, if you know your derivatives, this is super easy, right? So the derivative of e to the 3x is 3e to the 3x. I need the second derivative. I think I'm going to need at least to the 4th, because, again, I wanted a 4th degree, so I'm planning on that right now. 9e to the 3x. Third derivative, 27e to the 3x. Fourth derivative. Once we get to 4, we usually stop doing tally marks. I like Roman numerals, but you can just put a 4 up there if you want to. So now let's see if we can get us all lined up here. I want to evaluate all of these at 2. So this is 3e to the 6th, this is 9e to the 6th, this is 27e to the 6th, and this is 81e to the 6th. So this is going to cover, remember, let's go back to the formula real quick. This is going to cover all of these constant pieces, right? That's what I'm doing. So all I need to do now is attach or tack on the factor that makes it the power series. So we're going to multiply this one by technically x minus 2 to the 0, right? So I'm going to go ahead and mark that out because it's just 1. I'm just trying to make sure that y'all understand that's what we're doing. And then we're going to do times x minus 2 to the 1 times x minus 2 squared over 2 factorial times x minus 2 cubed over 3 factorial. And that's going to be times x minus 2 to the 4th over 4 factorial. That does give me a 4th degree, which is what I expected. So all I need to do is write it out in polynomial form. So we're going to say f of x is being approximated by the 4th degree polynomial. And we're going to start at e to the 6th. And we're going to add 3e to the 6th times x minus 2. And we're going to add, remember, 9e to the 6th and 3 to the 6th, those are just numbers, right? E to the 6th is a number. It's a constant. X minus 2 squared over 2 factorial plus 27e to the 6th x minus 2 cubed over 3 factorial. I need one more to make it a 4th degree. Let's see if I can squeeze that in here. 81, e to the 6th. Almost jumped past that. X minus 2 to the 4th over 4 factorial. All right. I do want to make a note to the side. So sometimes reducing factorials is convenient, but not required. Right, so let me explain to you what I mean by that. This 4 factorial is a 24. Sometimes, like especially if that number was a 24, sometimes I might just reduce those, right? If it was like a 48 or something, it would be really easy to reduce. So sometimes we kind of go through the process of reducing these to see a better pattern. Sometimes we just leave it as is. It's always accurate like this, but sometimes reducing it does make it a little cleaner. I am going to write down our steps really quickly. So kind of the first step in building a Taylor polynomial is to take the derivatives. I'm going to abbreviate some. Then we want to evaluate at the center. Then the third step, I don't really know how I have a better way to say this, is we want to tack on the power series factor, x minus c to the n over n factorial part, and then add all terms. Those are kind of the steps that we're going to use to build these Taylor polynomials.